So in terms of concept, you've learned everything you need to know about Newton's third law, and you can analyze a whole wealth of problems from inclined planes to pulleys and all that. So in principle, I can just leave you to it, and you can read the textbook, you can read all the examples and try to stare at a problem and figure it out on your own. But let me be nice to you, and I'll show you. I'll actually work out a few more examples, maybe two more. I'll think two popular ones, and meanwhile just comment, sort of do a narration along and show you how to approach it, and also throw in a couple of tips to make it easier for you when you attack the problems yourself. So example number 3 is also similar to example 4.13, I believe, in the textbook. And it's a very popular one, and almost one of the standard memes by now as well, is if I have a pulley with 2 boxes. Let's go through our favorite 3 and 2 kilograms boxes again. And let's ask the same thing. So we have a pulley. What I will have is a massless wheel and string rope connected, not strip, string, connected them together. And I will ask for both the acceleration of the system, and also the tension in the rope. Okay, so standard, pretty standard questions like that. So it's we'll still see how this is done. So you go back to the same thing, the very first step. Start with drawing a free body diagram. Okay, so the free body diagram, let me just directly draw on this, right? So this guy will have a weight for this, and it's also in contact with this, so it has a tension, right? So remember, ask yourself, what's touching the object and what's not touching it still gives a force. Well, only thing touching it is a tension, and the other thing is there's nothing else, so there's only weight that is left. Now notice big red bells should start flashing. Bells don't flash, but yeah, alerts start flashing and red lights start flashing, that you have duplicate variables, and immediately ask yourself, are they the same? Well, I definitely know that the weights are not the same. Let me put a prime over there. How about the tensions? Again, I've done enough of these problems at this point that they're probably the same, but just to be safe, let's make sure they're not first, and we'll argue that they are the same, right? Okay, so now we can write down the free body, the Newton's second law. So once you have the free body diagram, this procedure is pretty standard. You can probably take notes on your own. Step 1, draw the free body diagram. I'm just going to say this in words. Draw the free body diagram. Step 2, write for each object of interest, and then write down the Newton's second law for each object of interest. Find out if there's any variables that are the same or different, equate them, and solve the usually simultaneous equations. All right, so let's go ahead, right? So let's give them names, right? So we'll call this A and B, because the moment, notice this is almost second nature to me at some point, because the more you do it, the moment I write this, I know that I need to write another one, and now I need to differentiate them. So I better give them names of A and B, because I'll need to, right? This is for A. So this is the Newton's second law for A, and this is the Newton's second law for B. Okay, this type of pulley problem is so famous. There's a standard name. It's called Atwood problems. I believe first studied by this guy, where things having a pulley. Now, take a guess before I actually even solve for the acceleration of the system. First of all, this is 3 kilograms. This is 2 kilograms. Which way will it go? Right? You have a frictionless, massless pulley. Which way will it go? Well, this is heavier, right? So intuitively, this should go this way. So you can almost put in a direction that I believe it will go this way, and so that will go up and this will go down. Now, the next question is, even before we solve for the acceleration, of course, that's the goal, what do you think the acceleration would be? Would it be larger than g, the acceleration due to gravity, or smaller than g? Okay, so think about that. My intuition say it should be, the fall over here should be smaller than g, right? Because g means it's free fall, but now it's connected to something. and there's some sort of inertia over here. This is heavy, right? And think about it the other way. If both of them are 3 kilograms, this is not going to accelerate. It's going to stay the same, right? Or it's going to be moving at a constant speed. In any case, there's no acceleration. It's going to be 0. So if this is 2, if this is 0, so think about the extreme cases. If this is 3, there's no acceleration. If this is 0, there's nothing connected to it. If the string is massless, this is basically free fall. So if A is 0 kilograms, this would be G. The acceleration would be G, downwards, in the direction downwards, right? So it has to be somewhere between 0 and G, all right? Let's see. So now we apply Newton's second law. We write down the net force of A. Now we need to define an axis, right? The moment I go there, which way should I go positive? Which way should be negative? Let's again, if you're wise, you can actually go, hey, I know this is that's why I'm commenting on making a guess of which way it goes. I know this is going to go this way and this is going to go this way. Let me make this guy positive y go downwards and this guy's positive y go upwards if you're smart. However, I'm usually not. I just go with brute force and go like, you know what? Yeah, but I'm going to stick with positive y going up because that's what I'm comfortable with. And it will work. I'll show you. Both ways work. I will introduce 1 or 2 more minus signs, but as long as you're careful with it, basically in my approach, you just follow the rules, it will work. So here you go, okay, so upwards is positive, right? So the net force on A would be T minus W, not W minus T, right? Because that's positive, that's negative, all right? And now I can plug in numbers, but let me do this way as well. So net force on B this time it would be T prime minus W prime, right? Okay, so good. And is this the same? Now it's hard to see, right? So the trick over here, I'll need to introduce a new trick, is this. Whenever you see a rope going up and down like this, your goal is to, this is the trick. You stretch it out, take this. Does that make sense? You take this, stretch it out horizontally, and analyze the free body diagram as if it is this way, right? So imagine if I stretch out the rope. What's touching the rope? Well, this end is in contact. This end is this end, right? It's in contact with the 2 kilograms. So let me just displace the arrow a little bit so we can actually see what we're drawing. Yeah, I don't like that. Let's follow the proper rules from the center of mass. So yeah, I'll draw this here. So there's a tension on the rope by A, right? Due to this contact point. And due to this contact point is this contact point. So this side would produce a tension on the rope by B. Yes, I recognize it's bent, but you can actually unbend it and just analyze. It's pulling on this side. This guy is right. This mass is dragging it to the left. So that's why A on rope is this way, and B on rope is trying to pull it this way. Okay. And if this is a massless rope, then this is equal from the reasoning of the previous video. Right. Good. So and also this is the tension on A by rope. So let's specify it on A by rope. And this is the tension on B by rope. So on rope by B, on B by rope, that means by third law, that's identical to T prime. By third law, that's identical to T. That means by second law, these two are equal. So T is equals to T prime. So now we can start plugging numbers. All right. So let's do it here. T is equals to T prime, right? And what is, I still don't know what T is. I just know that this is the same T as that T. What is M? Let's start one at a time from the left. So we have 2. Now, how about the acceleration? I'm going to put that last, actually. And the weight, well, that's mg, right? 2g. And here we have the weight, which is 3g. Okay, and the mass is 3. How about the acceleration? Well, let's give it a name. Now, notice that's the acceleration. So this is the acceleration A. This is the acceleration of B. What can you say about both the magnitude and the direction? And first of all, the direction is, let's start with the easy one, right? If you have something confusing, start with what's easy. The direction is easier. The direction is opposite. Okay, good. How about the magnitude? Is it the same? What happens if they're not the same? If this guy is accelerating slower than this guy, the magnitude, right? So after 1 second, this is going to go up faster than this. Then the string is no longer taut, right? Now it's loose. Does that make sense? Probably not, right? It's going to probably go smoothly if this is a smooth pulley. Can that be larger than this? No, it's inextensible. So you cannot have this go faster, any faster than this. So the magnitude, by the argument from an inextensible rope, again, the reason why the magnitude of A is the same as the magnitude of B is due to the inextensible condition of the rope that makes sure these two magnitudes are the same. Let's treat this like a one-dimensional vector. Let's include a sign, but they're opposite direction, right? So whatever this value is, because I'm calling positive y this way, this is going to be negative of that, okay? So if I do an absolute value, yes, the magnitudes are the same, as you can see, but the direction is different. This is just in, the direction is opposite. This is in 1D, so I can just use negative like this. One more time, let's say this guy is moving at 5 meters per second upwards. This guy is going to move downwards at 5 meters per second. So if I call y positive y upwards, then this is going to be negative. This is yeah. So the magnitude of this, if this is 5, right? So then sorry, if this is 5, this guy will better be -5 for this to work, right? Yeah, if you like, you can put the minus sign on this side. So if this is slightly more obvious. If this is 5, then this guy better be -5. All right. I'll just put it here. It doesn't matter, and I'll call this A. All right, because so what I'm saying is I'm calling A of the acceleration of A. I'm calling negative of the acceleration of B A. So in other words, this is a lazy way. We always write this, but put the second thing in parentheses. This is a lazy way of saying AB equals to minus A. I'd say A equals to A and AB equals to minus A. Okay. All right. So AA is A, as I just wrote there, and AB is minus A. How many unknowns do I have? How many equations do I have? I have 2 equations and 3 unknowns? No, 2 unknowns, because G is known. G is just a constant. I'm going to keep it as G, just to be clear in a second. All right, so now again, you can use substitution, elimination. I'll encourage you to get used to elimination when things are easy like this. You see a T and a T, so you should beg yourself to subtract them, right? You've got to do what you got to do. You have to subtract them to get rid of the T. All right, so get used to this idea. So what will result is this subtract this. So I'll have 2A subtract -3A will equals this subtract this, but I can first subtract the T. So that goes away, and then this subtract this. So -2G subtract -3G. Did I get something right or wrong? Let's see. Yeah, that looks good to me. Now, if you're uncomfortable with this, let me also briefly explain to you, right? This is the fact that you can do this, right? Take this and add this or subtract. If you have something equal something and something else equal to something else, you can take the left-hand side, either add them, subtract them, multiply them, divide them. You can do whatever you like, as long as you do the same thing to both sides. The reason is in the power of addition. So if I have like an apple equals to something, and orange equals to something, then an apple plus orange is equals to this thing plus this thing. And if I subtract, it's the same story, right? Just as more concrete, if I have apple equals to half an apple plus half an apple. Orange equals to half an orange plus half an orange, right? Then an apple plus orange is equals to apple plus half an apple, or I can do it in different orders. I can do it half an apple plus half an orange plus half an apple plus half an orange. These would add up. It will always equal, right? Slightly more logistically. For example, this is equals to $2. This is equals to $3, right? So I can add them. So you have apple plus orange is equals to $2 plus $3, right? So if something is equal to something, this is a power in equal, right? You can subtract them as well. So let's go through numbers, right? 3 equals to 2 plus 1, 2 equals to 1 plus 2. If you like, you can subtract both sides, right? So I have 3 minus 2 is equals to, I can take this thing, subtract this string, or I can do them individually. I can take, for example, I can do it like this, right? And you will see that this equals to 1. Or I can just take this, subtract this, subtract this. But when this subtracts this, these cancel. So I just have 2 subtract 1. So that's just 1. Of course, that is equal, right? So as long as something is equal to something, you feel free to do the same thing to both sides, all right? So just a quick refresher of why this works. And I'm sure you already know you can do this, but just in case you don't know why that works and just memorize as a rule, it's because of that. All right, back to the math. This is easy. 5a minus 2g plus 3g, that's just g. So what does that tell me? It tells me a is 1/5 of g. Is that what we expect? Right, so A, let's get clear which direction it is. A is the same direction as acceleration of block A, and it's negative of, so just to be clear, right? So if we properly answer our question, AA is 1/5 of G, right, in the upwards direction, and AB is 1/5 of G in the downwards direction. Right, so we write that down. That's exactly what we expect. It might be surprising. It's 1/5, right? That's interesting. So that's 0.2 essentially. That's 2 over 10, so 0.2. So that's 20% of the rate of free fall. If you have an additional thing here, it slows it down to 1/5 or 20% of the acceleration, right? So we actually learned something new about this situation. This is like Atwood machine pulley thingy, right? And you can also go ahead and calculate the tension. You know what? I'm going to let you do that. And in fact, just so I don't bother you with a separate video of something pretty easy, I'll let you do it yourself. And I've quickly done the math, and I think I got T equals to 2.4 G. Okay, so you can check that. That much newtons, and you can check that if you got the same answer. All right. So in this situation, if you want this rope to work, your rope better be able to support 2.4 G. So if G is, remember the just horizontal example 2 when I'm just pulling the rope, what was the tension? That was 6 newtons, right? How many newtons is this? If G is 10 roughly, then I need 24 newtons. So I actually need I need a rope that can actually hold 24 newtons, right? So I learned something new about the physics as well. So with learning this math, you see when you go out and buy a rope, in order to do this, you better buy a rope that doesn't snap under 24 newtons of tension, okay? And you can think about why the tension in this case of the rope is much larger than the horizontal case. And you can think about the intuition and the physics behind that.